Welcome to the 680 review session. Let me just see if I can maybe improve the focus a bit. So here are the problems that you have sent me that I'll be going over. In fact, this is the order that I'll be going through them, so you can speed through the video if you wish. And again, the solutions I write up during this video, I'll post up separately. So from Ross, here are the problems: parts of 4.1, 4.5, 4.15, parts of 8.1, 8.5, 8.7, 9.3, 9.5, 9.9, 10.7, parts of 10.9, parts of 10.11, parts of 11.1, and from the additional homework, parts of 3, then 5, 9, and parts of 10. Let me give the focus one more shot at improving. I think this shouldn't be too bad. So let's begin. So page 1, first problem is 4.1H. And what we're looking at is the union from n equals 1 to plus infinity of the closed intervals 2n to n plus 1. And what we're supposed to be computing is this bounded above? If so, give 3 upper bounds. Well, if we look at this set, and again, I advise you very, very, very strongly, draw pictures, write out a few special cases. So in other words, what this is, it's starting at n equals 1. It's the interval from 2 to 3. Union, when n is equal to 2, the interval from 4 to 5. Union, when n is equal to 3, the interval from 6 to 7. Union, when n equals 4, the interval from 8 to 9. So in other words, if you look at the real line, this set contains the interval from 2 to 3, the interval from 4 to 5, the interval from 6 to 7, etc., etc., etc. Notice this set is not bounded, so you can't find any upper bounds. So this one, not bounded. Again, this is problem 4.1H. Hopefully that one wasn't too difficult. Next set might be a little more interesting. This is 4.1I. This is an intersection from n equals 1 to infinity of the intervals from -1 over n out to 1 plus 1 over n. And again, if we're going to figure out what these sets, if we're going to figure out if these sets have upper bounds, we need to know what they look like. So let's start writing this out. When n equals 1, this is the interval from -1 to 2. Union, when n equals 2, it's the interval from -1/2 to 1 plus 1/2. Intersection, when n is equal to 3, it's from -1/3 out to 1 plus 1/3, etc., etc., etc. So if we're going to figure out if this set has upper bounds or not, we need to know what it looks like. Well, even if you don't know what the set looks like, what you know is you take the set from -1 to 2, and then we're going to start taking intersections. So in other words, this final answer lives inside the interval from -1 to 2. So any upper bound for the interval from -1 to 2 will be an upper bound for this entire set. So Looking for least upper bounds, we need a better understanding of what this set looks like. But all we're interested in is upper bounds. This set, so this entire set, is smaller than this closed interval. So some upper bounds would be 2, 3, 4, etc. Because in particular, any number bigger than or equal to 2 is an upper bound. Well, that answers the question that the book had, but let's try to understand what this set looks like a little bit more, because I think people were having some trouble with the concepts of nested intervals. We have the closed interval from -1 to 2, intersected with this interval, intersected with this interval, and notice these endpoints keep moving further and further and further to the right, and they can be made as close to 0 as you want. Similarly, these intervals are getting closer and closer and closer to the number 1. So if you think about it, the closed interval from 0 to 1 seems to be contained in every one of these that you're intersecting, because this number is always less than or equal to 0, and this number is always greater than or equal to 1. But if you're less than 0, at some point you're going to be excluded here. If you're more than 1, at some point you're going to be excluded here. So it looks like the intersection is just a fancy way of saying the closed interval from 0 to 1. So it turns out if you were actually interested in the least upper bound, which the book isn't, but when we're curious that the book is, this set looks like it's the closed interval from 0 to 1, which means 1 would be the least upper bound. There are, without doing a thorough investigation, lots and lots and lots of upper bounds. A more thorough investigation tells us that the least upper bound is 1. Two more parts of 4.1 people were interested in. There's 4.1, part R, where the setting question is an awful lot like the one we just looked at. The intersection from n equals 1 to infinity of the open intervals. Well, it's not the same as the one we just did, so I'll be a little bit more careful. Okay. We're taking the intersection of these open intervals. So let's see what we're intersecting. When n equals 1, this looks like 0, 2. When n is equal to 2, this looks like 1/2, 3/2. When n is equal to 3, this looks like 2/3, 4/3. When n is equal to 4, this looks like 3/4, 5/4. And then we keep intersecting. So if we look at this on the number line, we start off with 0, 2, and then we keep on intersecting. So in particular, the answer here, this set is smaller than the open interval from 0 to 2. So if you wanted 3 upper bounds, since this set is smaller than 0, 2, any upper bound for the set 0, 2 would be an upper bound for this set. So for example, just like before, the numbers 2, 3, and 4 all turn out to be upper bounds because they're upper bounds for this particular set. But let's be a little bit more curious than that. Let's actually see if we can figure out exactly what this set is and see if we can figure out the least upper bounds. Now, notice, no matter what n is, this number is a little bit less than 1, and this number is a little bit more than 1. So every one of these intervals is an open interval containing the number 1. But notice, as n gets large, the length of this interval decreases. The difference between 1 plus 1 over n and 1 minus 1 over n is 2n, which goes to 0. In other words, these intervals keep shrinking down to a length of 0. Well, if the lengths are shrinking down towards 0, you can't have two different points in here, because eventually the intervals would be smaller than the distance between those 2 points. So the bottom line is you can have at most 1 point in this intersection. Now notice, you're not guaranteed there's anything in the intersection, because the nested interval property only applies to closed sets, and these are open sets, so maybe there's something in here, maybe not. Well, we determined that the number 1 is here, and we determined that you can contain at most 1 point. Therefore, it turns out that this set is just a fancy way of saying the single point 1. Now, this is much, much more than the book asked for. The book just wanted upper bounds. The final answer is much smaller than this particular set. So any upper bound for the open interval 0, 2 would work. All of these work. If you wanted the least upper bound, which we don't at this point, this set is a fancy way of saying the number 1. So this is just a set containing 1 element. So 1 would certainly be the least upper bound. Okay. Last part of 4.1 that I will investigate is part W, where you're looking at all points or all numbers of the form sine of n pi over 3, where n is a natural number. Well, again, we can answer what the book wants, although we could go even into greater depth. Every number here is a value of the sine function. So the biggest it can possibly get is 1. That means the biggest this can possibly get is 1/3. Well, we don't even have to deal with the fact whether this ever hits 1/3. What we notice is this is always less than or equal to 1/3. Well, if we're looking for 3 upper bounds, then all we have to do are take 3 numbers greater than or equal to 1/3. So like 1/3, 2/3, 3/3, they're all upper bounds. They'll do the trick. If we wanted to investigate more thoroughly for the least upper bounds, then notice the biggest the sine function can ever get is 1, and this actually hits the number 1. Because if you, well, let me take that back. Let's think about this. When we look at the graph of the sine function, okay, at 0 copies of pi, it's 0. At 1 copy of pi, it's 0. At 2 copies of pi, it's 0. So in fact, the numerator here is always giving you the value of 0. In other words, the sine can take on lots of values, but the sine of integer multiples of pi are always, again, we can go on forever here, but this is sine of 1 pi, sine of 2 pi, sine of 3 pi, sine of 4 pi, sine of 5 pi. In fact, the set in W is just a very, very fancy way of saying the single number 0. So the set in W is just the number 0. So if you were looking for least upper bounds, since this set only contains 1 point, the least upper bound would be 0. So this actually isn't what somebody asked, but again, kind of interesting. This particular set turned out to just be the single number 1. This particular set just turned out to be the single number 0. So you didn't have to do all that to figure out upper bounds, but you did need to do that if you were looking for least upper bounds. So that takes care of problem 4.1. Let's move on. Next problem people were interested in was 4.5. Proving these things are kind of difficult if you've never thought about them before, but again, let's give it some thought. Let S be a non-empty subset of R that is bounded above. Fine. Prove if the supremum of S belongs to S, and notice since the set is bounded above, sup S or supremum of S in this case means the same as the least upper bound. Prove that if the least upper bound belongs to S, then the supremum is the max. Your proof should be very short. Okay, so I'm not going to write all the details, but I'll talk through all of it. We want to prove that if the supremum of a set is an element of the set, then the supremum is the biggest element of the set. Now, there are lots of sets that don't have maximums, like open intervals, but we want to prove that if the supremum is in the set, then the supremum is the max. So we need to show two things. I mean, how do we typically show equality in mathematics? We have to show that the supremum is less than or equal to the max, and that the max is less than or equal to the supremum. Well, let's think about this. The maximum element of S is the biggest element of S, so it's bigger than or equal to any other element of S. So max S greater than or equal to any element of S, but in this particular case, the supremum belongs to S. So if the max is bigger than or equal to any element of S, well, that's certainly true of the max, but the supremum is one of the elements of S, then the max is greater than or equal to the supremum. So these are written backwards, but they mean the same thing. So this takes care of this half. In the other direction, the supremum is an upper bound for the set. So the supremum is bigger than or equal to every element of the set. Well, since max S belongs to S and sup S is an upper bound, that means the sup is greater than or equal to the max. Again, supremum is bigger than or equal to every element of the set. Since the max is in the set, the supremum is bigger than or equal to the max. So notice, again, these are written backwards from here and there, but both halves have been shown. Hopefully that's clear. And again, I think that satisfies the book's idea that it should be a short proof. So that was 4.5. Next one. Let's see where we are. 4.15. This is one, again, if you don't write a lot of proofs, this is sort of an awkward problem. Okay. We're looking at two real numbers, A and B. We want to prove if A is less than or equal to B plus 1 over n for every natural number n, then A is actually less than or equal to B. Well, the intuition should make sense. Okay. A is less than or equal to B plus 1. A is less than or equal to B plus a half. A is less than or equal to, say, B plus 1 over a million. A is less than or equal to B plus 1 over a trillion. No matter how tiny a number you add to B, you still beat A. It certainly seems likely that A can't be bigger than B. So I don't know how formal I'll do this, but I'll start kind of with a picture. So suppose not. What that would mean pictorially is that A, well, it means A is bigger than B. In a picture, A would be here and B would be here. So there's a positive difference between A and B. Let's call this thing epsilon. Well, remember, you can find an integer, say t, such that 1 over t is less than epsilon. So let t be a natural number such that 1 over t is less than epsilon. Remember, the least upper bound property said that no matter how small epsilon is, again, I'm letting epsilon be a minus b here, which is a positive number. I can find a t such that 1 over t is less than epsilon. That means if you take b and you add 1 over t, you don't make it all the way to a. Again, since we're defining epsilon to be a minus b, if you add epsilon to b, you get to a. If you add something less than epsilon, you don't make it all the way to a. So for this particular positive integer, b plus 1 over t is less than a, as you can see from the picture. But we're told that this holds for every single positive integer. So in particular, it holds for the positive integer t. So a is less than or equal to b plus 1 over t. Well, since this is a strictly less than sign, that means that b plus 1 over t is less than b plus 1 over t, and that's certainly a contradiction. So again, this was, and still is, 4.15. So again, kind of formal. I think it makes a lot more sense if you just start drawing a picture. You suppose not, that means A is actually bigger than B, so there's some positive distance before them. If you add 1 over some really big number, you don't make it all the way to A, so you don't make it all the way to A, but we were given this inequality leading to a contradiction. That takes care of 4.15. Next, we move to 8.1b. 8.1b is we want to prove, and we want to prove that the limit as n goes to plus infinity, the book didn't write that, but I tend to use that symbol, of 1 over n to the 1/3 is equal to 0. Well, intuitively, and from our experiences, as n gets large without bound, n to the 1/3 gets large without bound. Since the numerator is 1 and the denominator increases without bound, the whole thing approaches 0. And I'm going to stop for a second because I don't like the focus here. Hopefully that's not too bad. So, and again, I'll write large. So what we have to show is, for every epsilon greater than 0, there exists some capital N in the positive integers, such that if you take something bigger than capital N, we have the nth term in the sequence minus 0 is less than epsilon. Well, let's do some scrap work. If we look at 1 over n to the 1/3 minus 0, that's just 1 over n to the 1/3. Somehow, we want this to be less than epsilon. Or maybe I should put an extra step in. This would be less than 1 over n to the 1/3. And we want this to be less than epsilon. But we'll just do a little algebra here. This is the same as 1 over n being less than epsilon cubed. And that's the same as 1 over epsilon cubed being less than n. So if you wanted more of a proof, you would say, given epsilon greater than 0, let capital N be bigger than 1 over epsilon cubed. Again, if epsilon is a small number, 1 over epsilon cubed is going to be a really, really, really small number, and this fraction is going to be really big. So, whenever little n is bigger than big N, we now have, I'll just point to these inequalities. So, no matter what epsilon you pick, there's a cutoff point such that if you pass the cutoff point, we have this chain of inequalities saying that the limit of this sequence is indeed 0. So that was B. Let's move to D. Here we want to prove that the limit as n goes to plus infinity of n plus 6 over n squared minus 6 is also 0. Again, intuitively we know this because when n is large, the top looks like n, the bottom looks like n squared. N over n squared looks like 1 over n. 1 over n goes to 0. But in terms of scrap work, for formal proof, I know that n plus 6 over n squared minus 6 looks like 1 over n. But the numerator here is bigger than n, the denominator here is less than n squared. So although this looks like 1 over n, if you start plugging these numbers into your calculator, this thing is going to be bigger than 1 over n. But let's take something that looks like 1 over n that we can handle, like 1 over 2n. And here's the question. Is 1 over 2n always bigger than this quantity? Well, notice that's the same as if you cross multiply, since things will be positive, at least if n is bigger than 2. Cross multiplying, you get, this is the same as 2n squared plus 12n being less than n squared minus 6. Let's see if I did that correctly. Multiple, okay, and that's the same as n squared plus 12n plus 6 being less than 0. So it looks like I didn't do that right. So again, that's why we call it scrap work. So maybe I shouldn't be looking at 1/2 n. In fact, in hindsight, I certainly shouldn't. This thing isn't less than 1 over n. It's certainly not going to be less than 1/2 1 over n. Again, that's why they call it scrap work. So let's see if this is less than 2n. That's the same as, 2 times 1 over n. That would be the same as n squared plus 6n being less than 2n squared minus 12. Again, I'm comparing n plus 6 over n squared minus 6 times, comparing it to 2 times 1 over n. Cross multiplying, that's the same as n squared plus 6n being less than 2n squared minus 12, which is the same as 0 being less than n squared minus 6n minus 12. And that happens fairly frequently. Again, it may not happen at 1, it may not happen at 2, it may not happen at 3, but again, it's pretty clear that n squared minus 6n plus 12 eventually becomes always positive. So here's the proof. Given epsilon greater than 0, well, I need to write out more of the scrap work. If I look at n plus 6 over n squared minus 6 minus 0, I want this to be less than epsilon, but this is again the same as n plus 6 over n squared minus 6, at least when this is positive. This is less than 2 times 1 over n, and this will be less than epsilon if I made the choice of, well, if I want this to be true, I would take 2 over epsilon to be less than 1 over n. So here we go. Given epsilon greater than 0, let n be a natural number such that, again, the n should be there, such that n is bigger than 2 over epsilon and n squared minus 6n minus 12 is positive. So then if n, little n is bigger than big N, we have this is equal to this, is less than this, is less than that, and we have the proof that we want. Again, the whole idea was this thing looks like 1 over n, but it's not less than 1 over n. And it's certainly not less than 1 over 2n, which was a silly thing for me to try. But it's certainly less than 2 times 1 over n. But I can certainly make 2 times 1 over n easily less than epsilon. So given any epsilon greater than 0, pick an integer such that n beats 2 over epsilon, and these things are positive. Then we get the inequalities that we need. So that takes care of 8.1D and B also. Again, if you have additional questions on a problem like that, certainly contact me and we can go over that. Next one is, let's see what page I'm up to of notes. Page 7, 8.5. Okay. Consider the 3 sequences AN, BN, and SN such that the SNs are sandwiched between the ANs and the BNs. The ANs approach S. The BNs approach S. We have to prove that the S sub n's approach S. The book calls this the squeeze lemma. Lots of other books will call this the sandwich lemma. Namely, if you're sandwiched between 2 things and they're both approaching S, so does this. Well, here's the intuition. You can make the ANs as close to S as you want just by going far out in the sequence. That's what it means to converge to S. The BNs can be made as close to S as you want. Again, that's what it means for them to converge to S. Well, if the A sub n's are close to capital S, and eventually the B sub n's are close to S, that means these 2 things are close to S. Well, if these 2 things can be made as close to each other as we want, that means these 2 things can be made as close to each other as we want. Because the distance between the S sub n's and the A sub n's are less than the distance between the B sub n's and the A sub n's. So, if I can make S sub n and A sub n as close as I want, and I can make A sub n and capital S as close to each other as I want, then I can make these as close to each other as I want. So, a little bit of scrap work. I want to make the distance between the nth term of the sequence and S as small as I want. However, notice I can kind of rewrite this as notice with a little bit of algebra, these are the same. This measures how far the S sub n term is from the A sub n. This measures how far the A sub n term is from the S term. But notice I can make these things as small as I want. So if you were given an epsilon, you could eventually make these things less than epsilon over 2. I can make these things eventually less than epsilon over 2, which means I've made this distance less than epsilon, which is what I want. So for proof, given epsilon greater than 0, there exists a capital N in the natural numbers such that whenever we're past the nth term in the sequence, we have this is less than epsilon over 2 because the A sub n's converge to S, and this is less than epsilon over 2 because, again, these two things can be made as close to each other as we want. Again, if you want to go over this problem with me, I can certainly go into more details. Then we have this chain of inequalities, that the nth term in this sequence differs from the number S by less than epsilon, and that means that this sequence really does converge to capital S. Again, if you want, I could go into more detail at some point why this can be made less than epsilon over 2. But again, the basic reason is if this can be made close to S and this can be made close to S, then these two things by the triangle inequality can be made as close to each other as we want. Okay. There's a second part of this problem. That was 8.5a. There's a second part of this problem, 8.5b. Suppose S sub n and T sub n are sequences such that the absolute value of the S sub n's is less than the absolute value of the T sub n's for all n, and the limit of the T sub n's is equal to 0. You have to prove that the limit of the S sub n's is equal to 0. Well, I'll just write a little bit. If you want to show that the limit of the S sub n's are equal to 0, you want to show that you can make this thing less than epsilon. But this is the same as the absolute value of S sub n. And we know that the absolute value, let me just stare at this for 1 second. We know that since the T sub n's go to 0, that means this can be made less than epsilon. But the absolute value of the S sub n's is, I just got to check that they're okay on the sign here, because I don't want to mess up in case the T sub n's are positive. No, well, the T sub n's have to be positive because they're greater than the absolute value of the S sub n's, and the absolute values are always positive. So we want this to be less than epsilon, but we know that this is less than epsilon, and we know that the absolute value of the S sub n's is less than or equal to the absolute value of the T sub n's. So here's the story, without writing all the details. I want to show that this sequence converges to 0. That means I can make this absolute value less than epsilon. But this absolute value is the absolute value of the S sub n's. We're given that the absolute value of the S sub n's are less than or equal to the absolute value of the T sub n's. And we know we can make the absolute value of the T sub n's less than epsilon. So if you were going to write a more formal proof, given epsilon greater than 0, choose n such that this happens. And if this happens, then all this happens. So again, you're certainly, again, you can certainly contact me if you want more details, but again, given epsilon greater than 0, there exists a capital N in the integers such that if you're past the nth term of the sequence, we have the absolute value of the t sub n's are less than epsilon. And then the rest follows. That takes care of 8.5. Next, for 8.7, show that the following sequences do not converge. Again, we have cosine of n pi over 3. We have negative 1 to the n over n. And we have sine of n pi over 3. Oop, better rewrite that. The 3's in the wrong spot. Sine of n pi over 3. Well, if we think about these things, for this one, we're looking at cosine of pi over 3, cosine of 2 pi over 3, cosine of 3 pi over 3, etc., etc., etc. If you think about this, this sequence will have cosine of 3 pi over 3, which is cosine of pi, cosine of 6 pi over 3, cosine of 9 pi over 3. In other words, as you go down the line here, this is going to have cosine of pi, which is negative 1. Further down the line, it's going to have cosine of 2 pi, which is 1. Further down the line, it will have cosine of 3 pi, which is negative 1. A little later, it will have cosine of 4 pi, which is 1, etc., etc., etc. In other words, this sequence has an infinite number of negative 1's occurring. It will have an infinite number of plus 1's occurring. A sequence that has an infinite number of minus 1's, if it converged to anything, it would have to be negative 1. But this sequence has an infinite number of 1's occurring. That means if anything, it converged to 1. Well, if you can make an argument that this converged to 1, and if you can make an argument this converged to negative 1, then it doesn't converge to anything. Let me jump down to part 3 because it's probably the same sort of, well, things might be similar for the sign. Let's see what we can come up with. We have, let's draw the sine graph. We have sine of pi over 3 when n is equal to 1, sine of 2 pi over 3, sine of 3 pi over 3, sine of 4 pi over 3, sine of 5 pi over 3, sine of 6 pi over 3. So we don't quite have the clear cut here of you're going to keep having 1's and negative 1's occurring, but you're going to continue to have, let's see what this is. Sine of pi over 3 is sine of 60 degrees. That's a root 3 over 2. Down here, you're going to have negative root 3 over 2. So, whereas this sequence continues to have negative 1, blah, 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 1, blah, 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 negative 1, blah, 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 1. This sequence is going to have square root of 3 over 2, etc., etc., negative root 3 over 2, etc., etc. Then this is going to repeat. This is going to repeat. So this particular sequence is going to have an infinite number of square root of 3 over 2's popping up. It will have an infinite number of negative root 3 over 2 popping up. Well, if root 3 over 2 pops up an infinite number of times, it's the only candidate for a limit. If negative root 3 over 2 pops up an infinite number of times, it's the only candidate for a limit. If there are 2 candidates for being the limit, then there's no limit at all. So again, This keeps on taking values of -1 and 1 and maybe some others, so there's no limit. This keeps taking values of √3/2 and -√3/2. Maybe there are some others, so there's no limit. And for B, this sequence is -1, 2, -3, 4, -5, 6, -7, 8, etc., etc., etc. Notice, I mean, lots and lots of reasons that this thing doesn't converge. In particular, it's unbounded. So the alternator here didn't mess you up because it already wasn't going to converge because it's already unbounded. So that takes care of 8.7. Okay. Moving on to page 9 of the notes and moving on to problem 9.3 from the book. Suppose the limit of a sub n is equal to a and the limit of b sub n is equal to b, and s sub n is a to the n cubed plus 4an over bn squared plus 1. We want to prove that that limit is, well, you can see what it's supposed to be. Let's play with it. Okay, so we're given the a sub n's converge to a, the b sub n's converge to b. The sequence s sub n is defined as a sub n cubed plus 4a sub n over b sub n squared plus 1. We want to show the limit, and this is intuitively what we already know, that the limit of this is you just replace this by a, you just replace this by a, and you just replace this by b, but it wants us to run through why the limit theorems allow us to do it. So the limit of s sub n is the limit of these terms. Now, one of the theorems of the book says the limit of a quotient is the quotient of the limits. So let's take the quotient of the limits, provided that these limits exist and the denominator isn't 0. So we'll have to check that along the way. Next thing is, this is a sum. Theorem of the book says the limit of the sum is the sum of the limits. Here we have a sum. One of the theorems in the book says the limit of the sum is the sum of the limits. Now, this is a product, a sub n times a sub n times a sub n. The book says that the limit of this product is the product of the limit. So, 3 copies of this limit. This is a product. The book says the limit of the product is the product of the limits. The limit of 1, well, that's just a constant sequence, so that's always 1. And again, this is true provided both of these limits exist. This is true provided both of these limits exist. This is true provided these individual limits exist. But we're given that this limit is a. We're given that this limit is a. We're given that this limit is b. So again, at every point, you could apply the limit theorem as long as the individual limits exist. And notice, yes, these individual limits did exist because again, the limit of, the limit is the limit of the quotient as long as these exist. But at every step in the way, when we come down here, we see, yes, these limits do indeed exist. That is, this limit here exists as a, this limit exists as a, this limit exists as b, and so on and so on. In other words, what you would just do naturally is you would just plug in a, and b, this breaks it down piecewise, piecewise, piecewise. This sort of is the justification for just plugging in. Okay. So that takes care of 9.3. Moving to 9.5. 9.5 says, suppose the first term of the sequence is 1, and the nth plus first term in the sequence is the nth term squared plus 2 over 2t to the n. And assuming that it converges, let's find the limit. So we're told the limit exists. We'll let t denote the limit. So the limit of the left-hand side is the limit of the right-hand side. Now, the limit of the original sequence, the limit of the t sub n's, is the same as the limit of t sub n plus 1. It's just that the sequence is always one step ahead. So since we're told the limit of the original sequence exists, this is equal to L. And the problem we just did basically said, as long as we know the original sequence converges to L, we can just plug L into here as long as, again, the top has a limit, the bottom has a limit, and so on and so on. But the top will converge to L squared plus 2. The bottom will converge to 2L. So if L is the limit, L has to satisfy this equation. Well, this means 2L squared is L squared plus 2. That means L squared is equal to 2. That means L is plus or minus the square root of 2. So that says the only possible candidates to be the limit are plus or minus the square root of 2. But again, notice the first term in the sequence is positive. If you plug a positive number in here, you're going to get a positive number back. Again, if t sub n is positive, then tn plus 1 is going to be positive. So essentially, this is an informal induction proof. Since the first term is positive, so is the second. Since the second term is positive, so is the third. Since the third term is positive, so is the fourth. There's nothing you're doing here that's going to take a term in the sequence which is positive and flip the next term. So since all the terms in the sequence are positive, there's no way the terms in the sequence can possibly be getting close to negative the square root of 2. So the only two candidates to be the limit are plus square root of 2 or negative square root of 2, but negative square root of 2 can't possibly be the limit. So if the limit exists, it has to be the square root of 2. That takes care of 9.5. Moving on to 9.9. 9.9 says, suppose that there exists some positive integer n sub 0 such that the s sub n's are less than or equal to t sub n's when we're past this n sub 0. We want to prove that if the limit of the s sub n's is plus infinity, then the limit of the t sub n's is plus infinity. If the limit of the t sub n's is negative infinity, then the limit of the s sub n's is negative infinity. And if the s's and the t's have the same limit, then the limit of the s sub n's is less than or equal to the limit of the t sub n's. Okay, so here's the story. In part A, we want to show that the limit of the t sub n's are plus infinity. That means we have to show that no matter how big a number you pick, eventually all the t sub n's are bigger than this. So we have to show for every capital M, no matter how big a number you pick, there exists a cutoff point such that if we're past the cutoff point then the absolute value of the t sub n's, well, not even the absolute values, then the t sub n's are bigger than capital N. So no matter how big a number you pick, there's a cutoff point, such that if you're past the cutoff point, all the terms are bigger than M. So here's what we do. Proof. Given M bigger than 0, let capital N be such that the S sub n's are bigger than M. And we know this exists because the S sub n's go off to plus infinity. And, okay, so such that if N is bigger than N, the S sub n's are bigger than N. And at this point, notice eventually the T sub n's are bigger than or equal to S sub n's. So again, we know eventually the S sub n's will be bigger than capital M because these go off to plus infinity. And we're given that eventually the T sub n's beat the S sub n's. Okay, so therefore, the T sub n's are bigger than or equal to the S sub n's, are bigger than M, and we get what we want. Again, the intuition is these numbers are eventually bigger than M, these numbers are eventually bigger than this M, so that does the trick. I'm going to leave part B because I'm thinking if you understand how part A works, then you should also be able to see how part B works. So I'll just leave that. The trickier part might be part C. Okay, so let's move to part C. Prove that if the S's have a limit and the T's have a limit, then the limit of the S's is less than or equal to the limit of the T's. Well, what we often do is for these things, so I'll let S be the limit of the S sub n's. I'll just start off with some scrap work here. And I'll let T be the limit of the T sub n's. And let's suppose not, and let's see if I can get a proof to fall out of this thing. So, suppose not means that the T's have a smaller limit than the S's. Okay, now, here's the thing. I'll let the distance between S and T be epsilon. And then I'll look at, say, epsilon over 3 moved forward here. So this is T plus epsilon over 3. And then I'll move backwards over here, S minus epsilon over 3. Now let's see. Why did I do this? Well, because eventually all the terms of the sequence live within that epsilon over 3 of T. So in other words, eventually no term in the T sequence is going to pass here. Similarly, all the terms in the S sequence can eventually be made close to S. So none of them are going to be passed here. So at some point, no term in the T sequence gets beyond here, no terms in the S sequence gets beyond here, but that means there are terms in the S sequence that are bigger than the terms in the T sequence, and that's a contradiction. So here I think is my proof. Okay, suppose not. Then T is less than S. T being the limit of the T sub n's, S being the limit of the S sub n's. Okay. Let epsilon be S minus T, which is a positive number. So there exists capital N in the natural numbers such that if you take any n bigger than capital N, we have that the S sub n's differ from S by less than epsilon over 3. In other words, all the terms in the S sequence live to the right of S minus epsilon over 3, and the T sub n's minus T are less than epsilon over 3. So again, if you're past this wall, all the T's are to the left of here, all the S's are to the right of here. So this means, therefore, the S sub n's are bigger than S minus epsilon over 3, which is bigger than T plus epsilon over 3, which is bigger than the nth term. So again, all the S's are bigger than S minus epsilon over 3, but S minus epsilon over 3 is bigger than T plus epsilon over 3, and T plus epsilon over 3 is bigger than all the T sub n's. But this is a contradiction because we have that S sub n is less than or equal to T sub n, and here we have S sub n is more than T sub n. So, I hope that's enough detail. I hope that makes sense. That takes care of 9.9. Moving to chapter 10. Okay, for chapter 10, we're starting with 10.7. Okay, let S be a bounded non-empty subset of R such that the sup is not in the set. Prove that there's a sequence of points in S such that the limit of the S sub n's is equal to the sup. Okay, so picture. Okay, here's the sup of S on the number line. So again, it is, since the set is bounded, this is the least upper bound. No smaller number is an upper bound. So let's look at sup of S minus 1. Let's look at sup of S minus 1/2. I'll just mark them there. Let's look at sup of S minus 1/3. Let's look at sup of S minus 1/4. And why am I looking at these? Eventually, when you look at the original sequence, so when you look at the sequence, none of these are upper bounds because sup of S is the least upper bound. So no matter how much you shrink sup of S by, it's not going to be an upper bound. So if you look at the sequence, there's going to be a point that gets past sup S minus 1. Don't know which one that is, but there's some point. Now let's look at the rest. If you look at the rest of the sequence, eventually all the points in the sequence get past sup of S minus 1/2. So you can pick one. But eventually all the points in the sequence get past sup of S minus 1/3. So pick one. So here's, again, what you're doing is you pick a point in the sequence that gets past sup of S minus 1, because eventually they all do. You pick a point in the sequence that gets past sup of S minus 1/2, because eventually they all do. You pick a point in the sequence that gets past sup of S minus 1/3, which they all do. And lo and behold, if you think about the sequence that you just picked, the first one is within 1 of S. Rather, the first one we picked is within 1 of sup S. The next one is within 1/2. The next is within 1/3. The next is within 1/4. So this is a sequence which converges to the sup of S. Again, hopefully the words and the pictures made sense. Again, hope that works out for you. That took care of 10.7. Okay, next is 10.9 B and C. Okay, 10.9 B and C. We're given a sequence that S1 is equal to 1 and Sn plus 1 is n over n plus 1 times Sn squared, for n being bigger than or equal to 1. So nobody really asked to find S2, S3, and S4. What people want to know is show the limit exists and then show the limit has to be equal to 0. Well, to get a sense of the limit existing, well, let's see what we have here. To get a sense, S2 is, you plug in 1 over 2 times 1 squared. So that's 1/2. S3 would then be 2 over 3 times 1/2 squared. 2 over 3 times 1/2 squared looks like 1/6. Let me think about this again. If you plug in 1, S2 is 1/2 times 1 squared. If you plug in 2, S3 is 2/3 times 1/2 squared. So what it appears is that we're decreasing and bounded. That's what it appears to be. So in terms of the being bounded, well, if it's decreasing, we're fine because we start at 1. Notice everything we're doing here keeps us in the positives. At no point do we become negative. So you start at 1, and if it's decreasing, you keep on decreasing, but you're always bigger than or equal to 0. So that means every point in the sequence would be in the interval from 0 to 1. So if you're decreasing and always positive, you're always giving terms in here. So if you're decreasing, then you're bounded, and decreasing bounded sequences always have a limit. So we have to show decreasing. Well, the easiest way is this number is always less than 1. So as long as S sub n is less than or equal to 1, you get Sn plus 1 is a number less than 1 times a number less than 1 times Sn. So in other words, as long as Sn is less than or equal to 1, to get to the next term, you multiply by something less than 1, so you're shrinking. So now what we need is that S sub n is always less than or equal to 1. But if you look at it, if one of these terms is less than 1, then the square is less than 1, and this number is less than 1. That's going to make this number less than 1. So if you want to write out more details, or we just talk this way, notice I'm talking my way through a mathematical induction proof. If S sub n is less than 1, then its square is less than 1. You multiply by a number less than 1, then the next one is less than 1. So whenever a term in this sequence is less than 1, the next one is going to be less than 1. So all the terms are going to be less than 1. Since all the S sub n's are less than 1, the way you get the next term is you take the previous term and multiply by something less than 1. So this is decreasing. So you could write out more details, but the bottom line is this is a decreasing bounded sequence, therefore it has a limit. So what is the limit? Well, let's take the limit of both sides here. The limit of Sn plus 1 is the limit of n over n plus 1 Sn squared. The limit theorems say, okay, the limit of the S sub n plus 1s is the same as the limit of the S sub n's. The limit of the product is the product of the limits. So this approach is 1. This approach is L squared. So L is equal to L squared. That means 0 is L squared minus L, which is equal to L times L minus 1. In other words, the only candidates are L equals 0 or L equals 1. But notice, having proven that this is decreasing, once the second term is 1/2, all other terms are less than 1/2. If all terms are eventually less than 1/2, there's no way that the limit could possibly be 1. So we know the limit exists. The only candidates are 0 and 1. Eventually, or very quickly, all the terms are less than 1/2. So 1 can't be the limit. So lo and behold, the limit is indeed 0. So that takes care of part C. Okay. Next problem that someone had, or someone requested, and again, I appreciate you sending in your requests, was for number 11, rather 10.11. Okay, for 10.11, T1 is equal to 1. Tn plus 1 is 1 minus 1 over 4 n squared times Tn. And we want to show the limit exists. Well, again, presumably, it's the way we've been doing all these problems. The way we're going to get the formula to exist, the limit to exist, is to be monotone and bounded. Well, to see if it's monotone, we need to get a sense of what the next few terms look like. T2 is, you plug in 1. When you plug in 1, you get 1 minus 1/4, and Tn is 1. So you get 3/4 of 1. So if we hope it's monotone, we're looking for decreasing. Let's look at T3. When you plug in 2, T sub 3 is 1 minus 1 over 16. So it's 15 over 16 times 3 over 4, or 45 over 64. Well, this was 48 over 64. This is 45 over 64. It seems to be decreasing. So, is it decreasing? Well, notice 1 over 4n squared is always positive. So 1 minus 1 over 4a squared is always less than 1. So the way you get to T2 is you take T1, multiply by something less than 1. The way you get to T3 is you take T2 and you multiply by something less than 1. The way you get the next term in the sequence is you took the previous term and multiply by something less than 1. So if I continue to multiply by things less than 1, things continue to shrink. So again, you could write a more formal proof, but the basic idea is, given a term in the sequence, you multiply by something less than 1 to get the next term in the sequence. That's going to make it bounded. Notice you got a whole bunch of positive numbers that are decreasing, so in particular, they're bounded by the number 0. So every term in the sequence lives in the interval from 0 to 1. So this is a decreasing bounded sequence, so lo and behold, the limit exists. Now, if I remember correctly, finding what the limit is for this one is really, really tricky, and the book kind of has fun with you on this, so I think I only asked you for part A. But the point is, this sequence is decreasing and bounded, therefore, the limit exists. And the final question from Ross that was posed by you was, let's look at the sequence So this was 11.1b. We were given the sequence a sub n equals 3 plus 2 times -1 to the n. And they're saying give a subsequence that is constant and talk about how you choose them. So if we look at the sequence, depending upon whether n is odd or even, this will be negative or positive. That means you're either subtracting 2 or adding 2. So when n is 1, you're subtracting 2. When n is 2, you're adding 2. So this sequence just alternates 1s and 5. If you want the selection function, well, if you're always taking an odd subscripted term, you're always 1. So if you took g of n, well, what's an increasing function that when you plug in any integer gives you odds? Well, 2n minus 1 should do the trick. So when you plug in 1, you get the first term. When you plug in 2, you get the third term. When you plug in 3, you get the sixth term. When you plug in 5, or whatever, 4, you get the seventh term. This produces the sequence 1, 1, 1, 1, 1, etc. If you just want to get the even number terms, that would just be h of n equals 2n. So for n equals 1, you get the 5 here. When n equals 2, you get the fourth term. When n equals 3, you get the sixth term. When n equals 4, you get the eighth term, and so on and so on and so on. So if you want the selection function, 2n minus 1 would be the selection function that gives you 1s all the time. 2n is the function that gives you 5s all the time. And that takes care of the problems from Ross. Now let's move on to the other problems that I gave you, the additional problems. So, first one, I think someone wanted, they said part 2 number 11, but there is no part 2 number 11. So, from the additional problems, I'm assuming that someone wanted number 3, part 11, since again, there was no number 2, part 11. So this says, if A and B are non-empty subsets of R, such that the sup of A is less than the sup of B, then B contains an element which is an upper bound for A. And we want to figure if this was true or false. So let's think about this. They're non-empty subsets. B has a bigger sup, then B contains an element which is an upper bound for A. So let's think for a second. Okay. One case is that the sup is plus infinity. Well, if the sup is since the sup of A is less than the sup of B, sup of A is finite. Well, since the sup of B is plus infinity, it increases without bound. That means you can pick something which is bigger than the sup of A and is therefore bigger than every number in A. So in other words, in the case that the sup of B is plus infinity, then we automatically know that the sup of A is finite. Just pick a number in B, since again, B does not have an upper bound. Just pick a number in B. So pick some B in capital B such that B is bigger than the sup of A. Since again, B is not bounded in this case, and A is bounded. Now, second case is where the sup of B is finite, and therefore the sup of A is also finite. Okay. And so now let's see. Here on the number line is the sup of A. Here on the number line is the sup of B. And if the sup of B is bigger, there's some positive distance between these. So there's some positive distance epsilon between them. Let's take half of that. If this is the sup of B, then there is an element of B that gets passed here. Because if there was no element of B that got passed here, this would be a smaller upper bound. So what we can say is, in the case where the sup of A and the sup of B are both finite, let epsilon be the difference between the two. The sup of B minus the sup of A. Now, if you look at the sup of B minus epsilon over 2, here's the sup of B minus epsilon over 2. There's some B such that B is bigger than the sup of B minus epsilon over 2. Again, if you back up any small positive distance, this is not an upper bound for B, therefore there's an element of capital B which is bigger than it. So there's some little b that beats the sup of B minus epsilon over 2, but the sup of B minus epsilon over 2 beats the sup of A. Well, since the sup of A is an upper bound for A and little b beats it, this means there is indeed an element of B that beats every element of A. So we broke this down into two cases. One case where the sup of B was plus infinity, the other where the sup of B was finite, but in both cases, B does contain an element which is an upper bound for A. Next one. Someone was interested in problem 5. So additional problems number 5. Look at the intervals, the open intervals 0, 1 over n, and the closed intervals from 0, 1 over n. Find the intersections. Well, so if I'm intersecting all of these, first I take the set from 0 to 1. Then I intersect it with 0 to 1/2. Then I intersect it with 0 to 1/3. Then I intersect it with 0 to 1/4. Well, notice, obviously the intersection has to live somewhere between, has to be contained in 0, 1 because we're intersecting it with more. But no matter how small a number you pick, you can find an n that 1 over n is smaller than it. So it's going to be left out. So if you take any number bigger than 0, eventually it's going to be left out. Because again, you're intersecting with things like 0, 1 over a million, 0, 1 over a billion, 0, 1 over a trillion. No matter how small a positive number you take, you can find an n that this is even smaller. So no number is going to be in all these intersections. So in this case, the intersection is the empty set. Because no matter how small a positive number you take, eventually this set is going to leave it out. And the same exact situation is held here, except that you're taking endpoints, which means 0 is in every one of these sets. Notice the length of these sets is approaching 0, so there's no way more than one point could be in the intersection. But the nested interval property says there is indeed going to be something in the intersection. And notice in this case, the intersection is not the empty set, but the number 0. So again, this doesn't violate the nested interval property, even though the intersection is empty, because the sets are not closed intervals. And this doesn't violate the nested interval property, because the nested interval property says there should be something in the intersection, and there is, the number 0. So that takes care of number 5. Okay. Moving on to number 9 from the additional problems. In trying to prove that a suitable sequence S sub n converges to L, suppose that for a particular epsilon, we can find a suitable capital N, such that little n being bigger than capital N implies that the absolute value of S sub n minus L is less than epsilon. Okay. Then, pick one of these words. Then any larger or smaller capital N will also work for this value of epsilon. Well, again, suppose you came up with n equals 100. That means as long as you're past the 100th term, you're fine. Well, that also means as long as you're past the 200th term, you're fine. Because if you're past the 200th term, you're certainly past the 100th term. And you could certainly say, well, what happens if you're past the 500th term? Well, if you're past the 500th term, then you're certainly past the 100th term, so that's fine. So it looks like if you're taking larger n's, that's fine. And again, if you think about it, if your cutoff point originally was 100, if you went backwards to a cutoff point of 50, that might not work. So in 1, if you took any larger n, that would work. Next one. Then the same n will work for any larger, smaller. Pick one of the 2 words in bold to make the sentence true for epsilon. So suppose capital N will keep everything within 1/2 of the limit. Well, if it keeps things within 1/2 of the limit, then it certainly keeps things within 1 of the limit, or 2 of the limit, or 3 of the limit. But it might not keep it within 1/10 of the limit. So, in other words, if n works for a value of epsilon, it will work for larger values, because again, like if you were within 1/2 of the limit, then you're certainly within 1 or 2 or 3. But you might not be within 1/10. So, n will work for any larger value of epsilon, but again, as you pick smaller values of epsilon, you might have to change n. So in this case, not only is it larger n, but larger epsilon. And then I should go back and check later that I didn't make any typos on this one. So for the first one, if a value of capital N works, any larger one will work. And if capital N works for a certain epsilon, it will work if you make epsilon bigger, but it might not work if you made epsilon smaller. So in both cases, the answer is larger. And our final problem is, from the additional problems, is 10 parts 2, 3, and 4. Okay, so for number 2, provide an example or explain why no example exists. In problem 2, S sub n converges, T sub n converges, and the sequence converges. Well, that one, so for part 2, that one is false. That there's no way you can add a convergent sequence and a divergent sequence and get something that converges. And the reason is, if you take convergent sequences and add or subtract them, you will get something that converges. So in other words, if the S sub n plus T sub n's converge, and since the S sub n's already converge, then the T sub n's converge. So in other words, If the S sub n's plus the T sub n's converge, then the T sub n's would be the difference of two convergent sequences to make it converge, which is a contradiction. So, no, you can't find S sub n converging and T sub n diverging such that the sum converges. For 3, sequence that converges. Oh, sorry. Okay. Oh, I read that one properly. 3. A sequence converges where all the terms are non-zero and the sequence 1 over S sub n diverges. Well, it is true that that can happen. Example, if you let S sub n be 1 over n, then 1 over S sub n is equal to n. Well, this sequence converges. All the terms are non-zero, but this sequence diverges. So it is possible that the sequence converges, but the reciprocals diverge. Again, the only way it will happen is if the originals converge to 0. And finally, number 4, an unbounded sequence S sub n and a convergent sequence T sub n such that the sequence is bounded. And again, that will not happen. So, and let's take a look. Is it possible that, again, the S sub n's can be unbounded, the T sub n's are convergent, and the difference is bounded? Well, here's the story. The S sub n's are equal to the S sub n's minus T sub n's plus the T sub n's. Okay. We're given that the S sub n's are unbounded. And is it possible that the T sub n's can converge and that the S sub n's minus T sub n's are bounded? So here's the situation that we're wondering about. Can you have an unbounded sequence and a convergent sequence such that the difference is bounded? Well, in that case, this unbounded sequence would be a sum of these two sequences. But every convergent sequence is bounded. So that would mean you have an unbounded sequence, the sum of two bounded sequences. That can't happen. If you add two bounded sequences together, you're going to get a bounded sequence. So again, the reason that this can't happen is the T sub n's are bounded. That would say the S sub n is the sum of two bounded sequences, and the sum of two bounded sequences is always bounded. So false. You can't find an example that does this. Well, that's everything you sent in. Hopefully I will get the technology to work properly that you can see this shortly. And again, if you tune into this, I hope it was helpful. And if you have any additional questions you would like to send to me, please do. Again, I hope this was helpful, and I hope to have this posted. Well, if you're viewing this, I've obviously posted it. So have a great day, and any further questions, we'll stay in touch. Thanks.